Spy Derivative Man, back talking to you about the chain rule challenge problems. Now, how does Superman eat his cereal in the morning? With a Super Bowl! So the first thing we're going to do is review the chain rule. All this is saying is that if you have a composite function, a function within a function, what you're going to do, if you're taking the derivative of that, you take the derivative of your outer function, so the derivative of f of g of x, times the derivative of your inner function, g prime of x. Can we all agree that the Spider-Mans with Andrew Garfield weren't that good? It's example time. Now example 1 says find the derivative of the following function. So here we have f of x is equal to the cube root of x squared minus 1 squared. Now we said anytime you take the derivative of a function with a radical, you want to change that so it's a rational exponent. So the cube root of x squared minus 1 squared, we can change that so it's x squared minus 1 to the 2/3 power. Your root goes in the denominator of your exponent and the power, your exponent, goes in the numerator. Now what we can do is we can take the derivative, and here, this is going to require the chain rule because we have a function within a function. Our innermost function, we're going to set equal to u, so u is equal to x squared minus 1. That's our innermost function. That means our outer function will be u to the 2/3 power. Now the chain rule says you take the derivative of your outer function. So that's going to be 2/3 u to the negative 1/3 power. When you subtract 1 from 2/3, you get negative 1/3. So again, derivative of your outer function, 2/3 u to the negative 1/3, times the derivative of your inner function, which would be the derivative of x squared minus 1. Now, we said the derivative of your outer function was 2/3 u to the negative 1/3. And don't get confused when I substitute x squared minus 1 back in for u. Now what I can do is take the derivative of my inner function, x squared minus 1, and I get 2x minus 0, or just 2x. I can then take that 2x, multiply it to the 2/3 that's out front. I can move my x squared minus 1 to the negative 1/3 to my denominator to make it a positive exponent. And then a 1/3 power is the same thing as a cube root. So I change that, and I'm done. You try! Okay, so again, we want to simplify. We have a rational function here, but what we can actually do to make this easier to take the derivative of, because that's what we're doing, we want to take this denominator and move it to the numerator. So instead of being negative 7 over 2t minus 3 to the second power, we can have negative 7 times 2t minus 3 to the negative second power. Now, this function is way easier to take the derivative of. When I take the derivative here, I'm going to take this negative 7, and I'm going to move it out front by the constant multiple rule. That way I don't have to deal with it till the end. It's going to be a little bit easier. Now, as you can see, I'm taking the derivative of this function, and I have a function within a function. So I'm going to have to use the chain rule. The chain rule says I'm going to take my innermost function, 2t minus 3, set it equal to u, and then my outer function then would be u to the negative second power. Now, chain rule wants us to take the derivative of our outer function, which would be negative 2 u to the negative 3rd power, times the derivative of our innermost function, times the derivative of 2t minus 3. Don't forget that negative 7 that was out here. So I'm now going to simplify this. The negative 7 times the negative 2 is going to give me positive 14. Over here, the derivative of 2t minus 3 is going to be just 2. And then I take that 2, multiply it to the 14 that was already out front, and I get 28. I then take this 2t minus 3 to the negative 3rd power and move that to my denominator to make it a positive exponent, and I'm done. Now, example 2, we want to find the derivative of this function right here. So we said anytime you're taking the derivative of a function that has a radical in it, we want to change it so it's a rational exponent. So instead of the square root, we're going to write this as 1 minus x squared to the 1/2 power. Now we're taking the derivative of a function, x cubed, times a function, 1 minus x squared to the 1/2 power. So when we do that, we require the product rule. And the product rule says we must take the derivative of our first function, so that would be the derivative of x cubed, times our second function, plus our first function times the derivative of our second function. So the derivative of 1 minus x squared to the 1/2 power. Now over here, this one's going to be easy. Derivative of x cubed is just 3x to the second power. This stays the same. Here, the derivative of 1 minus x squared to the 1/2 power. We have a function within a function. So that requires the chain rule. So we're going to set u equal to our innermost function. U is going to be equal to 1 minus x squared. And then our outer function then would be u to the 1/2 power. The chain rule says we take the derivative of our outer function, so that would be 1/2 u to the negative 1/2 power, or 1/2 times 1 minus x squared to the negative 1/2 power, times the derivative of our innermost function, so times the derivative of 1 minus x squared. Now over here, the derivative of 1 minus x squared is going to be negative 2x. That negative 2x then I could multiply to this 1/2 that's out here, and I just get negative x. Then the negative x I multiply to the x cubed, and I get negative x to the 4th. Now here's where things get tricky. Pay attention. This is the hardest part for you guys to understand. each of these terms. This is a polynomial with two terms, 1, 2. What I'm going to do is I'm going to factor out an x squared, because each of these terms has an x squared, and I'm also going to factor out a 1 minus x squared to the negative 1/2 power. Now when I do that, from this term, I'm just going to get x squared. That's going to be the only thing that's left, because I factor out an x squared and a 1 minus x squared to the negative 1/2 power. So the only thing that will be left over here is x squared. This part, because I'm factoring out x squared, there will be a 3 remaining. Because I'm factoring out a 1 minus x squared to the negative 1/2, I actually have to add a 1/2 to this exponent and make it 1 minus x squared to the first power. So again, I factored out an x squared and a 1 minus x squared to the negative 1/2 power from each of these terms. Over here, all that was left was a 3 and a 1 minus x squared to the first power, because I factored out a negative 1/2. Think about it. If I were to distribute this now, the negative 1/2 power would add with the first power and give me a 1/2 power. If I were to distribute this here, I would get the exact same thing that I had over here. I do this because I can simplify this a little bit further now. I'll distribute this 3, and you see there are two x squareds in here. There's a negative 3x squared and a negative x squared. That becomes negative 4x squared. That stays in my numerator. This x squared stays in my numerator. 1 minus x squared to the negative 1/2 power I can bring to my denominator and write it as a radical, and I'm done. Example 3, I am taking the derivative of a rational function. We said anytime you take the derivative of any function and there's a radical in it, you want to change that so it's a rational exponent. So here, what I'm going to do is change the cube root to a 1/3 power. Now when I take the derivative of this function, it's going to require the quotient rule. The quotient rule says I take the derivative of my numerator times my denominator minus my numerator times my derivative of my denominator all over my denominator squared. Now derivative of x is just going to be 1. The derivative of x squared plus 4 to the 1/3 power is going to require the chain rule. Now my innermost function is going to be x squared plus 4. I set that equal to u. That means my outer function is going to be u to the 1/3 power. Now, chain rule says I take the derivative of my outer function, so it's going to be 1/3 u to the negative 2/3 power, or 1/3 times x squared plus 4 to the negative 2/3 power, times the derivative of my inner function, so times the derivative of x squared plus 4. Now, the derivative of x squared plus 4 is going to be 2x. I then multiply that to this x that's out front, and I end up getting 2x squared. That's where this comes from. Denominator, x squared plus 4 to the 1/3 power squared. Power to a power, you just multiply those exponents together. That's where the 2/3 comes from. Now, here's where things get interesting. As you can see, I have two terms in my numerator. In this term, I have x squared plus 4 to the 1/3 power. In this term, I have 1/3 times 2x squared times x squared plus 4 to the negative 2/3 power. Now, each of these terms has an x squared plus 4 to the something third power. What I want to do is I want to get rid of or factor out x squared plus 4 to some power. I also want to factor out this 1/3 because I don't like fractions within fractions. So I'm going to factor out a 1/3, and I'm also going to factor out whichever one is negative. So here it's negative 2/3. So I'm going to factor out an x squared plus 4 to the negative 2/3 power. Now here's what happens. If I factor out 1/3 x squared plus 4 to the negative 2/3 power, it's going to look something like this. Now let me walk you through what happened. Here, when I factor out 1/3 times x squared plus 4 to the negative 2/3 power, all that's going to be left in this term is the 2x squared. In this first term, though, if I factor out a 1/3, there is no 3 or 1/3 up here. So what I have to do, since I factored out a 1/3 from something that wasn't there, I have to put a 3 there now. Because if I were to distribute, they would then cancel out and there would just be a 1 up here. I also, because I factored out an x squared plus 4 to the negative 2/3 from a positive 1/3 exponent, I have to add 2/3 to this exponent. So this is going to become x squared plus 4 to the first power. So that's where this came from, x squared plus 4 to the first power. It's just like we did in the previous problem with the x to the 1/2 power when we factored that out. Because I'm factoring out x squared plus 4 to the negative 2/3 power from the positive 1/3 power, I have to add 2/3 to this exponent now, and it becomes x squared plus 4 to the first power. Now that I've factored this out, there's a couple things I can do. First, I can distribute this 3, and it becomes 3x squared plus 12 in here. I can also take this x squared plus 4 to the negative 2/3 power, bring it to my denominator, down here with this 3, and multiply it to this denominator here. Now, x squared plus 4 to the 2/3 power times x squared plus 4 to the 2/3 power is x squared plus 4 to the 4/3 power. Like bases, you add the exponents together. In my denominator, I now have a 3x squared and a negative 2x squared that I can combine into a positive 1x squared, and I'm done.
Spider-Man, Spider-Man, you turn.
Okay, so here, I'm taking the derivative of this function, and it's a function times a function. This function has a radical. Anytime I'm taking the derivative of any function and there's a radical, I want to change it so it's a rational exponent instead. So instead of the square root, I'm going to change it to the 1/2 power. Now I'm going to take the derivative of this function times this function. That requires the product rule. Product rule says I take the derivative of my first function times my second function plus my first function times my derivative of my second function. Derivative of x is just going to be 1. Derivative of 1 plus x squared to the 1/2 power requires the chain rule. My innermost function is going to be 1 plus x squared, so I set that equal to u. That means my outer function is going to be u to the 1/2 power. The chain rule says I take the derivative of my outer function, which is going to be 1/2 u to the negative 1/2, or 1/2 1 plus x squared to the negative 1/2, times the derivative of my inner function, which would be 0 plus 2x. Now let's go ahead and simplify this. 0 plus 2x is just 2x. I can then take that 2x, multiply that to the 1/2 that was out here, and that just becomes x. The x I can then multiply to this x, and I get x squared. Now again, look at what I have here. I have two terms. In this term, I have 1 plus x squared to the 1/2 power. In this term, I have 1 plus x squared to the negative 1/2 power. So what I'm going to do is factor out the negative one. So I'm going to factor out 1 plus x squared to the negative 1/2 power. If I factor out 1 plus x squared to the negative 1/2 power, it's going to disappear from this term. And in this term, I'm going to have to add 1/2 to this exponent and make it 1 plus x squared to the first power. And that's why I do that. Because now, the only rational exponent is going to be this one out here. In here, I have 1 plus x squared to the first plus x squared because it disappeared from here. The 1 plus x squared, we can just drop those parentheses. We can add these two together. It becomes 1 plus 2x squared. And the 1 plus x squared to the negative 1/2 power, I can bring to my denominator to make it 1 plus x squared to the positive 1/2, which is the square root of 1 plus x squared. And I'm done. Now example 4, we're again finding the derivative, and here we have a rational function that's being squared. So if I'm taking the derivative of this, you can see I have a function within a function, so this is going to require the chain rule. So I'm going to set u equal to my inner function, which in this case would be this rational function. So u equals 3x minus 1 over x squared plus 3. That means that my outer function then would be u to the second power. And the chain rule says you take the derivative of your outer function, which would be 2u to the first power, or 2 times 3x minus 1 over x squared plus 3 to the first power, times the derivative of my inner function, times the derivative of u. This part was easy. This part is going to be a little tougher. The derivative of my inner function, or the derivative of this rational function, I'm going to have to use the quotient rule. Now the quotient rule says I take the derivative of my numerator times my denominator, minus my numerator times derivative of denominator, all over my denominator squared. The derivative of 3x minus 1 is just going to be 3. The derivative of x squared plus 3 is going to be 2x. This is going to become 3, and this 3 I'm going to distribute to each of these terms and give me 3x squared plus 9. This is going to become 2x, which I can distribute to each of these terms and make it 6x squared minus 2x. Now here's what's going to happen. I'm going to multiply these two fractions together. So this I'm going to multiply over here. This I'm going to multiply over here. The x squared plus 3 to the first times x squared plus 3 to the second is going to be x squared plus 3 to the third, because when you multiply like bases, you add the exponents. Up here, when I distribute this negative, it's going to be 3x squared plus 9 minus 6x squared plus 2x. I can then combine like terms. The 3x squared minus 6x squared becomes negative 3x squared. And I can leave it like that if I want. If you really want to, you can FOIL this out and you're done. Now example 5, I'm taking the derivative of sine of 2x times cosine of 2x. Now anytime you take the derivative of two functions being multiplied together, you must use the product rule. So we're going to take the derivative of our first function times our second function plus our first function times the derivative of our second function. Now derivative of sine of 2x requires the chain rule. We have a function within a function. So u we're going to set equal to our innermost function, that's going to be 2x, and our outer function then would be sine of u. Same thing over here. We're going to set u equal to our innermost function, that's going to be 2x. Our outer function then would be cosine of u. So when we take the derivative of sine of 2x, we're going to take the derivative of our outer function, which would be cosine of u, or cosine of 2x, times the derivative of 2x. Here, again, using the chain rule, we take the derivative of cosine of 2x by taking the derivative of our outer function, so that's going to give you negative sine of u, or negative sine of 2x, times the derivative of 2x, the derivative of your inner function. Now, derivative of our inner function, derivative of 2x, that's just going to be 2. Now, let's simplify this a little bit further. Cosine of 2x times 2 is 2 cosine of 2x, times cosine of 2x is 2 cosine squared of 2x. Same thing over here. Sine of 2x times negative sine of 2x is negative sine squared 2x, times 2 is negative 2 sine squared 2x. Now I can factor out a 2 from each of these terms, and I have cosine squared of 2x minus sine squared of 2x. Now, if you recall from pre-cal, we have a double angle identity, which is if you have cosine of 2 times some angle, it's equal to cosine squared of that angle minus sine squared of that angle. So if I have cosine squared of 2x minus sine squared of 2x, that's the same thing as cosine of 2 times our angle, which in this case would be 2x. So cosine of 2 times 2x, or cosine of 4x. And you're done.
The itsy bitsy spider went up the water. You try!
Again, I'm taking the derivative of a function times a function. And when you do that, you need to use the product rule. So the product rule says the derivative of my first function times my second function plus my first function times the derivative of my second function will give me the derivative of this function. Now, the derivative of secant theta over 2, it may not look like it, but it requires the chain rule. I have a function within a function. So my u, my innermost function, is going to be theta over 2. That means my outer function is going to be secant of u. If I set u equal to theta over 2, that means secant u would be my outer function. Same thing over here. If I have tan of theta over 2 that I'm taking the derivative of, I have an inner function, theta over 2, so I'll set that equal to u. My outer function then would be tan of u. So when I take the derivative of secant theta over 2, I need to use the chain rule. I'm going to take the derivative of secant of u, my outer function, which gives me secant u tan u, or secant theta over 2, times tan theta over 2, times the derivative of my inner function. So times the derivative of theta over 2. Here, same thing. Derivative of tan of u will give me secant squared of u, or secant squared of theta over 2. And again, since I'm taking the derivative of tan theta over 2, it requires the chain rule. So I have to multiply by the derivative of my inner function, the derivative of theta over 2. Now, the derivative of theta over 2, you treat theta just like x. That's just going to be 1 over 2. Same thing over here. This is going to be 1 over 2. If I multiply the secant squared theta over 2 times the secant of theta over 2, I get secant cubed of theta over 2. And now each of these terms has a 1/2 and a secant theta over 2 that I can factor out. And I end up getting 1/2 secant theta over 2 times tan squared theta over 2 plus secant squared theta over 2. And you're done. Now, example 6, I'm again taking the derivative of, this time, cosine squared of 8 theta. Now, we know cosine squared 8 theta is the same thing as cosine of 8 theta squared. This just lets you know that you need to use the chain rule when you take the derivative here. So when we take the derivative, we have a function within a function. So we're going to set u equal to our innermost function, which would be cosine of 8 theta. That means that if u is equal to cosine of 8 theta, then our outer function would be u squared. So the chain rule says we take the derivative of our outer function, so that's going to be 2u to the first power, or 2 times cosine of 8 theta to the first power, times the derivative of our inner function. But look here, we now need the chain rule again, because if we take the derivative of cosine of 8 theta, we have a function within a function. So we're going to use chain rule again. We're going to set u equal to our innermost function, which would be 8 theta. That means our outer function, if u is 8 theta, would be cosine of u. So chain rule again says we take the derivative of our outer function, so that would be negative sine of u, or negative sine of 8 theta, times the derivative of our inner function, which would be derivative of 8 theta, which is just 8. So the derivative of cosine of 8 theta is going to be negative 8 times sine of 8 theta. Now we take that and we plug that in here for the derivative of cosine of 8 theta. Now we can simplify this a little bit further. Negative 8 times the 2 gives you negative 16. Now this should look somewhat familiar. Cosine of something times sine of something. We know that a double angle identity for sine is actually equal to 2 times sine of your angle times cosine of your angle. Now this doesn't necessarily look exactly like that, but if 8 theta is our a, and, well, we have a negative 16 out here, what we could actually do is write negative 8 times the quantity, 2 times cosine of 8 theta times sine of 8 theta. And now, yeah, it's kind of looking like that. So we can get negative 8 times, and it's going to be sine of 2 times our angle, which in this case would be 8 theta. So negative 8 times sine of 2 times 8 theta, which would be negative 8 times sine of 16 theta. And that is your derivative.
I'm sure some of you are wondering, why hasn't he put on the mask at all? Well, when you're 6'8" and you buy an adult large, it doesn't always fit. You try!
So we are taking the derivative of 5 cosine squared of pi t. Now, anytime you have cosine squared or sine squared, you want to rewrite that when you're taking the derivative as cosine pi t, the quantity squared. Makes it easier to recognize that you require the chain rule. So here, when we take the derivative, this 5, we can actually move out front of the derivative by the constant multiple rule. That way we don't have to deal with it till the end. Here, when we take the derivative, we require the chain rule. Just like we said, our inner function is going to be cosine of pi t. Our outer function is going to be this quantity squared. So we're going to set u equal to our innermost function, cosine of pi t. That means our outer function is going to be u squared. The chain rule says we take the derivative of our outer function, which can be 2u to the first power, or 2 cosine of pi t to the first power, times the derivative of our inner function, times the derivative of cosine of pi t. But now, here's where it gets tricky. The derivative of cosine of pi t also requires the chain rule. We have a function within a function, so we're going to actually set u equal to our inner function here, which is pi t. That means that our outer function is going to be cosine of u. And the chain rule says you take the derivative of your outer function, which is going to be negative sine of u, or negative sine of pi t, times the derivative of pi t, which is just pi times 1, or pi. We can then take this pi, multiply it to the negative 1 that's out front. We get our derivative is negative pi of sine of pi t. So we can then take this derivative of cosine of pi t, plug it in here. And now let's simplify this a little bit further. The negative pi, we multiply to the 10, and we get negative 10 pi cosine of pi t, sine of pi t. And again, you see the cosine of an angle, sine of an angle. And that should ring a bell. Sine of 2 times an angle is equal to 2 times sine of that angle times cosine of that angle. That's a double angle identity. So instead of having 2 sine of an angle times cosine of an angle, which is kind of what we have here, if we were to factor out a negative 5 pi, you can see we have 2 times sine of an angle times cosine of an angle. So instead of writing this, we can write negative 5 pi times sine of 2 times our angle, which in this case is pi t. Now 2 times pi t is just 2 pi t, and I'm done. Example 7, we're again finding the derivative, and here we have a function times a function. Now anytime you take the derivative of a function times a function, it requires the product rule. So we're going to take the derivative of our first function times our second function plus our first function times the derivative of our second function. Now this one is a challenge problem because each of these derivatives now require the chain rule. Here we have a function within a function, so we're going to set u equal to our innermost function, which is negative x. That means our outer function is going to be e to the u. Over here, I am taking the derivative of ln of x squared plus 2, meaning I have a function within a function, composite function. So I'm going to set u equal to my innermost function. U is going to equal x squared plus 2. That means my outer function is going to be ln of u. Now when I take the derivative here, using the chain rule, the derivative of my outer function, derivative of e to the u is just e to the u, or e to the negative x in this case, times the derivative of my inner function, so times the derivative of negative x. Here the derivative of ln of u is going to be 1 over u, or 1 over x squared plus 2 in this case, times the derivative of my inner function by the chain rule. Now the derivative of negative x is just going to be negative 1. The derivative of x squared plus 2 is just going to be 2x. Now this negative 1 times e to the negative x is going to be negative 1 times e to the negative x. This 2x then I can multiply here and bring it to my numerator. The e to the negative x I can bring to my denominator. Same thing over here. This e to the negative x I can make negative 1 over e to the x. And if I were to multiply these two together, then this will go to my numerator, and I'm done. If you wanted to make this so it's one fraction, you can multiply this by x squared plus 2 over x squared plus 2, but again, that gets a little nasty.
Thanos is a big purple idiot. You try.
Okay, we're taking the derivative of ln of this rational function, and this rational function is a hot mess. So let's try to simplify this a little bit further. We recall the properties of logs. There were 3 that we talked about: the product property, the quotient property, and the power property. This guy, we are going to use all 3 on. So let's start with the quotient property. You see that we have ln of something divided by something. That means we can split that up into 2 natural logs separated by a minus sign. So it's going to be ln of my numerator minus ln of my denominator. This guy over here, we now have ln of something times something. Now the product property of logs says we can split this up into ln of x plus ln of x squared plus 1 squared. Over here, we have the square root sign, and we're going to change that to a 1/2 power, a rational exponent. We do that anytime we're taking the derivative, and it helps us especially here because the power property of logs, we can now take this 2, move it out front of the ln. We can take this 1/2 and move it out front of the ln. Now we are ready to take the derivative of our function. And taking the derivative of this function, we're going to take the derivative of each term separately. The derivative of ln of x is going to be 1 over x. The derivative here, we're going to take this 2, move it out front, and just take the derivative of ln of x squared plus 1. Same thing here. We're going to take this 1/2, move it out front, and we're going to take the derivative of ln of 2x cubed minus 1. Now that we've done that, we are ready to take the derivative. So again, derivative of ln of x, that's just 1 over x. Derivative here, we are going to require the chain rule again. We have a function within a function. So we're going to set u equal to our innermost function. So u is going to equal x squared plus 1. That means that our outer function is going to be ln of u. Same thing here. U is going to be equal to our innermost function, which would be 2x cubed minus 1. That means our outer function is going to be ln of u. Now, for each of these, the derivative of ln is going to be 1 over u. So in this case, it's going to be 1 over x squared plus 1. By the chain rule, we have to multiply that by the derivative of our inner function, which would be the derivative of x squared plus 1. Same thing over here. Derivative of ln of u is 1 over u, which is 1 over 2x cubed minus 1 in this case, times the derivative of my inner function by the chain rule. Now, the derivative of x squared plus 1 is going to be 2x. The derivative of 2x cubed minus 1 is going to be 6x squared. We can then simplify this a little bit further. The 2x I can multiply this numerator. The 6x squared I can multiply this numerator. And I am done.